Hello and welcome. This is going to be our lecture video for the fourth quarter final review. We'll just be going over the answers here. Starting with number 1, in a solution, the substance being dissolved is known as the solute. Number 2, what makes a solvent dissolve faster in a solvent? There's 3 things that I want you to know. You can agitate the solution, you can increase the solution's temperature, or you can spread out the surface area by crushing up your solid, like we did with the Alka-Seltzer tablets. Number 3, the solubility of a dissolved solid length if the temperature of the liquid containing the solid decreases. So this is a direct relationship, so it's going to decrease if the temperature of the liquid decreases. Notice this is not always the same for gases, but that's a good rule of thumb for solids. There are solids that also violate that rule as well. That's why it's just a rule of thumb. Number 4, the maximum amount of a substance that can dissolve into a given quantity of a solvent at a given temperature is called its saturation point. That's right, saturation point there. Most common unit of measurement for volume is liters, especially with gas laws. We use liters for all of our calculations. Second most common would be milliliters, which is just a derived unit from liters. We can use lots of different things, but that is what we use in chemistry. Most common solvent is H2O, good old water. Almost always when we want to suspend some sort of solid in a solution, we use water because it's a good polar molecule. Correct units for concentration is molarity, which equals specifically moles per liter. Here, I'm going to write that one. All right, as you can probably tell, I do not have my tablet today for writing, so I'm not going to write too much, but molarity equals moles per liter. The point at which a solvent can no longer hold more solution is said to be saturated. Very similar question to above, but just saturation point versus saturated. When a solution has more dissolved solute than the solvent can normally hold, the solution is said to be supersaturated. And so, we can do that through like agitation. We can force more solvent to dissolve, but it will eventually settle out. And when we let it just sit, then it reaches its true saturation. All right. Number 10, when looking at a solubility graph, how do you know if a certain solution will be saturated? Supersaturated, simple. Our point is above the line. The point is above the line is what we're looking for there. Molar mass of the following compounds. Let me just calculate them really quick. All I'm doing is looking at a periodic table and adding them up, and I'm multiplying whenever I see a subscript to just that specific element's atomic mass. So there you go. There's all the molar masses. Notice the unit is always grams per mole for a molar mass. All right. Now we need to do some conversions. First, we're going to go grams to moles, and then we're going to go moles to grams. All right, in both of these, we need the molar mass of that compound. All right, so I'll pause again and show that work. All right, and there you go. It's the first one, it's 201.618 grams of NaCl. The second one, it's 2.2 moles of CO2. Notice when going from moles to grams, I have to multiply by the molar mass. When going the other direction, grams to moles, I divide by the molar mass. But as long as you set it up in a unit conversion bar, it should be easy to keep that all straight. All right, concentration is simply moles per liter. If I do 4.6 divided by 1.7, as simple as that, I get 2.7. And then the unit there is molar, so 2.7, and then it's always a capital M for molar. All right, for number 14, what will the volume of the solution be if you've got 0.398 moles of lithium fluoride and want to make a 2 molar solution? So 2 molar is 2 moles per liter. So I'm going to do 2 over x equals 0.38 and then rearrange it and just do the 2 divided by the 0.398 and get that it's 5.03 liters. All right. If now other way around, I want to make 0.65 liters of a 2.5 molar calcium chloride solution. How many grams of calcium chloride will I need? So first you have to figure out moles. So it's 2.5 moles per liter. So multiply that 2.5 by the 0.65 to figure out that I have 1.625 moles. But it now says I need grams. So I need to now multiply by the molar mass of calcium chloride. So multiplying by the molar mass of 110.978 grams per moles gives me 180.34 grams of CaCl2. All right, number 16, concentration, but my volume of solute is given in grams. Again, I need to convert that to moles, and then I'm going to divide it by 0.35 because that's what 350 milliliters is. And after converting, I got 0.47 moles, which I divided by the 0.35 to get 1.35 molar. All right, now we're doing a dilution. So the formula for this next one is M1V1 equals M2V2. So M1 is the 2 molar, V1 is the 250, and then M2 is the 12. So 250 times 2. I'm going to divide away that 12, and I get 41.7 milliliters. I didn't have to convert to liters. I can work in milliliters for this problem. And then you will add distilled water in that up to the 250 milliliter mark, and you'll get the correct concentration of 2 molar. All right, let's look at this graph for these next ones. Which compound is the most soluble at 40? So what I want to do is just sort of go up from 40 and see what the solubilities are. And the highest line right there is the NaNO3. So NaNO3. O3. Which compound is saturated if 50 grams of the solid is dissolved in 100 milliliters and the temperature is brought to 20 degrees Celsius? So I'll go up from the 20 and see that if I've got 50 grams, so I'm right here, I am above the line for both KNO3 and NaCl. So it's both KNO3 and NaCl. For C, which compound would be unsaturated if 100 grams is dissolved in 100 milliliters of water at 80 degrees Celsius? So I go up from 80 and then stop at 100, and I see that both KNO3 and NO3 are below the line. So both of those compounds are unsaturated, blue and yellow. At what temperature does potassium nitrate have a solubility of 87? So if I go over from where about I think 87 is, and I hit the line, that looks like it's 60 degrees Celsius. NaNO3, I've got 100 grams of it at 60 degrees. So I'm right here, 100 grams at 60 degrees. At what temperature will the crystals form? So we're going to let it slowly decrease until we hit the line. Right there, it looks like it's about 50 degrees. We'd be right over the 50 when crystals started to form. How much more potassium nitrate, so KNO3, will it take to saturate a solution that currently holds 25 grams at 100 degrees Celsius? So we are right here. We can go all the way up to here before we get saturated. And that distance there looks like 175 grams because it looks like the saturation point would be 200 grams at that temperature, but we already have 25 grams in there. Right, and then a solution containing 75 grams of sodium nitrate dissolves in 100 milliliters of water at 30 degrees Celsius. So the saturation point it could hold looks to be maybe like 87, but we only have 75. So this solution is unsaturated. All right, number 19, we've got a Beer's Law problem. If an unknown concentration absorbs 30 relative units, so we're going to go over from 30, what is its concentration? So then we go down, and it's 0.6. It says relative units, but it's probably going to be molar. That's our most common concentration unit. And then if the x-axis is molarity and a sample contains a 0.8 molar solution, what did you expect the sample to absorb? So we'll go up from the 8 and then over, and it looks like it's going to hit at 40 relative units. So just 40, and there's no real unit there. All right. When an acid is added to water, so now we're in our acid base, the amount of hydrogen ions increase. You could also say hydronium, which is H3O+. Additionally, acids can be defined as proton donors. What is a hydronium ion? How is it formed? So it's formed from a free proton bonding to water, and it's H3O+. All right, when a base is added to water, the amount of hydroxide ions increases. Additionally, bases can be defined as proton acceptors. All right. So use the pH scale to answer the following. Is borax acidic or basic? So it's right there. It is past 7, so that makes it basic. Is lemon juice more acidic than coffee? So we've got lemon juice right there. Coffee's right there. Lemon juice is further to the left, so it's more acidic than coffee. And what is the pOH of ammonia? So right here, we can see that ammonia has a pH equal to about 12. It's right on top of the 12. Well, that's not what the problem asks. It says the pOH. So we have to know that pH and pOH always add up to 14 and write that the pOH is 2. So you have to look, identify, and then also know that calculation. What is an indicator? What information can it give? So it's a chemical we add to a titration that tells us the end point of that titration because it changes color at a specific pH. 25, generic equation for a neutralization reaction. Let me write it. All right, so here's the generic form, and you should label it that the HA is the acid, the BOH is the base, BA is the salt, and then H2O is water. All right, number 26 asks us to balance some neutralization reactions. When I'm doing this, the first thing I think about is how many water molecules I can make, because I'll always take an H from the acid and an OH from the base and make a water molecule. Here I can make exactly one water molecule because I've just got one H and one OH. That makes one water molecule. All right, and then partner up the cation and the anion. So, which makes a salt. Typically, you put your cation first. In this case, that would be the potassium, and then your anion like that. Make sure all the electrons balance, but potassium has 1 to lose, fluorine has 1 to gain. So this is just a 1-to-1 to 1-to-1 relationship. All right, then this next one, how many water molecules can we make? Magnesium hydroxide donates 2 OHs, and the sulfuric acid donates 2 H's, so that's 2 water molecules, so 2 H2O. And then the magnesium and the remaining sulfate group, they can make their own salt. So magnesium, SO4, and everything else is balanced. So this is just a 1-to-1 to 2-to-1 relationship. All right, and the next one, I've got 1 hydrogen but 2 hydroxides. This needs to make an even number of water molecules, so I have to put a 2 here, and then I get 2 water molecules. Well, not necessarily even, it has to be a whole number of water molecules. All right, and then because I've got 2 of those will both partner up with the calcium to make a CaH2. And all of the subscripts work. So it's a 2-to-1 to 2-to-1 relationship. All right, now we need to label these all as acid, base, or neutral. pH of 3.4, that's going to be an acid. This next one is phosphoric acid, but because it's got a hydrogen at the front, we know that that's an acid. Products of a neutralization reaction, no surprise that these are neutral. POH of 12, that would mean a pH of 2, that's also acidic. Don't be tricked with the POH, this is very acidic. H2O is always neutral. KOH with an OH at the end, we know that's a base. Slippery is bases, sticky is acids. Soda has carbonic acid and fruit juices have citric acid, so both are acidic. Pink in phenolphthalein is basic. It's clear while it's acidic, and then it turns pink when it's basic. More protons than hydroxide, that's acidic. Equal amounts would be neutral. Next one is basic. Proton donor is an acid. Hydrogen ion or proton acceptor is a base. All right, label. So this is our acid. This is our base. This is water. And this is salt. All right, now we've got a titration. So 20 milliliters of hydrochloric acid was used using 0.5 molar sodium hydroxide. The indicator was phenolphthalein, and the base was in the burette. So net neutralization reaction, it's that plus that. We can just extend from here. It's going to become H2O plus NaCl. Initial volume in the burette, we have to read this. It looks like 9 point, I want to say 65. If you see 9.6, I'm fine with that. I think I see 9.65. It's not going to change our answer too much. And then final volume, looks like 24.15 is what I see. Remember, you can go one more significant digit. All right, total volume used. So we're going to just subtract those two numbers. 24.15 minus 9.65 gives us exactly 14.5 milliliters. To convert this to liters, you move the decimal place 3 times, and we get 0.0145 liters. So how many moles of NaOH were used? So here we need its concentration. It's 0.5 moles per liter equals X number of moles over 0.0145 liters. So 0.0145 times our concentration of 0.5 gives us 0.00725 moles. Original volume was 20 milliliters, which converts to 0.02 liters. And then the molarity, so we've got the moles of NaOH, which would be equal to the moles of HCl at the equivalence point. So 0.00725 divided by 0.02 gives us a concentration of 0.3625 molar. How do you know the titration was complete? Using phenolphthalein as the indicator. It is going to turn pink because phenolphthalein turns pink in base and we're adding base. So it's going to turn pink. Once it's slightly pink, we will say we are done. All right. Question 30 asks us for the molarity of hydrogen ions in a solution with a pH of 5.1. So the formula we need here is 10 to the power of the negative pH is going to give us the hydrogen ion concentration. So 10 to the negative 5.1, which we can plug into our calculator and get a number that we're going to express in scientific notation. So 10 to the negative 5.1 is 7.94 times 10 to the negative 6th. And your calculator might give you the scientific notation, or it might give you the number with a lot of zeros, and you got to convert it. It's just important that you know how your calculator works for problems like this. All right, 31. Which of the titration curves below best describes the change in pH for the titration of a weak acid with a strong base? So we're looking for something that starts acidic, so that's either B or D. But the key here is that because it's a weak acid and a strong base, the equivalence point will be slightly basic. And so that is answer choice B, where this equivalence point is up at like almost a pH of 9, meaning that at its equivalence point, the strong base is pulling up that pH to about 9. Another thing we see here is that it changes a little bit quicker at the beginning before it starts buffering. And let's see if I can think of one more reason why. So it starts acidic. It changes quicker at the beginning, and its equivalence point is more basic. So there's 3 reasons. All right. If I make a mixture of nitrogen and helium, do most helium atoms hang out at the bottom or the top of the balloon, or are they relatively evenly distributed? They're going to be evenly distributed. This is just a property of gases, is that they fill the container they're in. They don't congregate anywhere. Part of the reason is that they're bouncing around so fast that gravity has very little impact on them, and they're just going to end up wherever. What are 4 variables that affect how gases behave? What are the units for each? So just think of PV equals nRT. PV equals nRT, which is our ideal gas law. And so P stands for pressure. The unit we want to use for pressure is kilopascals. V stands for volume. The unit for volume is going to be liters. N stands for moles. The unit for that is just moles. And then T is temperature, and that one has to be in Kelvin. It's very important that we remember it's in Kelvin because we do a lot of chemistry in Celsius, but this is one case where you have to use Kelvin. What does STP stand for? That's standard temperature and pressure. The standard temperature is 0 degrees Celsius, which is 273 degrees Kelvin. And the standard pressure is 1 atmosphere, which is 101.3 kilopascals. All right, and now we've got some calculations. So with option A here, where we've got some sort of change happening, we're going to use our combined gas law. As seen here, but because pressure is held constant, pressure will cancel out, and then we'll just fill in what we've got. So the volume of 2.4 goes in for V1, divided by its temperature in Kelvin, has to be in Kelvin. Then I'll just, because I'm trying to solve for a temperature, I can multiply temperature to both sides and then divide both sides by this number I just calculated. So 1.1 divided by that number gives me a temperature of 151, and then the unit there is Kelvin. All right. B. Glass containers are currently at 35 degrees Celsius and exerts a pressure of 13.5. What will the temperature be if the pressure of the container is tripled? All right, let me set this one up. So again, I use the combined gas law, but this time volume canceled out because volume is held constant. We know that because it's a glass container, and that's not going to be very elastic. Now I'm solving for T2. I could cross multiply and then divide and get a 924 degrees Kelvin. So by tripling the pressure, the temperature goes way, way up. All right. All right, C is another combined gas law. So let's set it up in our P1V1 over T1 equals P2V2 over T2. All right, because temperature was held constant, we don't have to divide by temperature on both sides. This is just Boyle's law. I'm going to multiply the 340 and the 250, and then divide by the 900. All right, and I get 94.4 as my final volume, but I have to look back at what volume units I'm using, and that is cubic centimeters. So centimeters cubed, which is just equivalent to a milliliter. All right, letter D. A blimp contains 575 liters of helium gas. Here, it's another combined gas law, but now nothing is being held constant, so we have to plug in every number. So I'm going to do that now. All right, one thing to note is that I had to convert my temperatures to Kelvin before I plugged them all in. Now the right-hand side is just the left-hand side is just numbers, so I'm going to plug all of that in. 75 divided by 295. I get that the left-hand side is 186. I'll multiply that by the 243 to bring that over, and then divide by the 65.5 to bring that over, and I get 690 liters. So these changes caused it to expand to 690 liters. All right, now we have some ideal gas laws. So PV equals nRT. For N, we can use 8.314 as long as pressure is in kilopascals, which it's not right here. So I should multiply this by the fact that 1 atmosphere is equal to 101.3 kilopascals per 1 atmosphere. So 89 times 101.3 gives me 9,015. So now nRT, I'm just going to plug it into my calculator. For the temperature, I have to add the 55 to 273 to get it into Kelvin. And now I've got the number on my right-hand side, so I'll divide that by the 9,015.7 and get that my volume is a very small 0.00246. The unit for volume is always going to be liters for these kinds of problems. All right, this next one actually looks a little easier. We'll do the nRT side in our calculators first. So 0.00901 times 8.314 times 313. Then I'll divide by 0.802 to get my pressure, and it's 29.2, but I have to remember the unit for that is kilopascals. All right, the next ones are still just ideal gas law, but it gives it to us a little bit differently. So PV equals nRT. Just remember that, and then we're going to plug these numbers in where they're supposed to go. All right, when I plug those all in and divide, I get a temperature of 95 degrees Kelvin. Again, you have to convert your pressure here into kilopascals by multiplying by 101.3. Let's look at our next one. So again, pressure is given in atmospheres. So multiply by 101.3 to get kilopascals. Then we multiply by the volume, but we don't know the volume. So we're just going to store that number. We're going to do the nRT side. To get number of moles, we have a slight problem that we're given grams. So we have to convert this. So 5.03 grams divided by the molar mass of O2, which is going to be 15.999 times 2 for the 2 oxygens. Now I've got the number of moles is 0.15 times R, 8.314 times our temperature, which is 28 plus 273 to convert to Kelvin. And now we divide that all away from our pressure to get a volume of 0.257 liters. All right, and then the last one, very similar. We got to convert the argon, so 23.3, it's kilograms, but the periodic table only tells us grams per mole, so let's just multiply that by 1,000 to get the grams of argon, And then we're going to divide by the atomic mass of argon to get that this many kilograms of argon is 583 moles. So that's our N. I'm going to multiply that by 8.314, which is R. Then multiply that by 25 plus 273 to get Kelvin. There's our T. I get this very big number, 1,445,000. But now I'm going to divide away the volume of the tank, 212 liters, to get still a very high pressure of 6,816 kilopascals. So it's a very pressurized tank. All right. Now look up these definitions down here. There will be plenty of vocab on the test, but that's that for this lecture video. Have a good rest of your day.